Hi, Easy Contents here. I am certainly not the first person that is making a video about LED matrices, but I thought that it would be fun to dive into how they actually work and learn something new. I will be explaining in detail how the 64x64 RGB LED matrix works, and in the end I will make a small project based on ESP8266 where this LED matrix will be put to real usage. From the product code of this LED matrix, we can derive some features. P2.5 means that the pixel pitch is 2.5 mm, so the LEDs are spaced apart by that distance, and 64x64 pixels will give a dimension of the matrix of 16x16 cm. 32S means that only 1/32 of the LEDs will be turned on at the same time. So 4096 divided by 32 equals 128, and this means that only 2 rows will be lit when we will be addressing the matrix. I am guessing that 2012 is probably the manufacturing date, and 1.1 is the version number of the PCB. The pinout of the data connector is called hub 75, which is actually a standard 16-pin 2-row header. There is an input and an output connector that allow you to chain more matrices. It is externally powered by 5 volts using this JST VH3.96 connector. So let me start with a general explanation on how an LED matrix actually operates before we will zoom in onto the actual PCB design of it. This is a schematic of a simple LED matrix. I have drawn this diagram using the Falstad circuit simulator. The link is in the description. We can see here a shift register with data and clock inputs. It is directly wired to a latch that connects to LEDs on each row. The demultiplexer connects to each of the columns in the matrix. In real matrices, the row and columns are swapped, but unfortunately the Falstad circuit simulator did not let me rotate the latch component by 90 degrees. Eventually, this is just a matter of orientation. We start the cycle by specifying the LEDs that will light up in the first column. For that purpose, I will trigger the clock input manually. When the data input is set high, we toggle the clock pulse, and we see that the first data line of the shift register lights up. When we continue to trigger the clock input and toggle the data input, the register shifts and remembers what we specified previously. If we want to remember this configuration, we need to use the latch. To take a snapshot of the input register, we need to momentarily toggle the load row input. The latch functions as a memory, and if we change the shift register, it won't matter for the data that is already set on the latch. In order to activate the LEDs on the first column, we need to specify a value on the demultiplexer. The first row will have both inputs low, so its value is 0. When we activate the demultiplexer, the first row of LEDs will light up. To continue to the next column of the LEDs, we need to repeat the process. We also have to deactivate the first row by disabling the output of the demultiplexer. Then set the latch with the new values, specify the new row by changing the inputs on the demultiplexer, and activate it. In reality, this is happening very quickly as the clock pulses, and we do not see each column individually, but perceive it as if all LEDs light up simultaneously. When we go back to our 64x64 LED matrix and check the number of chips installed on the PCB, there are quite a bit more than we had in our example. As for the ICs, there are 2 main types. The first one is ICN2028, and it functions as a shift register and a latch. It is also capable of driving the LEDs with enough current. There are 24 pieces installed on the matrix. Each of them is capable of addressing 16 individual LEDs. So in total, 384 LEDs can be lit. When we divide that number by 3, as each LED consists of red, green and blue, we get 128 individual LEDs. This matches the specs that 2 rows of 64 LEDs can be visible at the same time. The next IC is SM5166P and functions as a demultiplexer with 3 inputs and 8 outputs. It is also designed as a LED driver to manage the power needed to light up the LEDs. 8 of these chips will be able to address 64 rows. There are also 3 74HC245 ICs. They connect directly to the HAP75 interface and function as buffers. The last IC on the board is another demultiplexer chip, 74HC138, and it helps in addressing the correct rows. The HAP75 interface can address up to 32 rows of LEDs by using 5 inputs A through E. That is enough, since we are always showing 2 rows at the same time. A, B and C connect directly to the address inputs A0, A1 and A2 of the SM5166 chip. D and E connect to the 2 inputs of the 74HC138 multiplexer chip and enable these SM5166 chips in groups of 2. In this way, it is possible to address a total of 32 lines that light up 2 rows of LEDs at one time. The clock input will pulse and shift in red, green and blue LED values into the ICN2028 chips using RGB inputs. There are actually 2 inputs for each color that latch in 64 values per shift register group. Triggering the LAT input will latch these values, and a signal to the output enable OE will turn on the LEDs that are latched. This cycle repeats over and over for each row. To get an idea on how all the chips are wired up, you can check the schematics of a similar panel that I found inside this GitHub repository. The link will be in the description. Let's create a small example project that shows the current date and time. For that purpose, I have decided to use the Wemos D1 Mini microcontroller board, which is equipped with an ESP8266 chip. If you still haven't done so, you will need to install the ESP8266 board inside the Arduino IDE that is based on the instructions on the ESP8266 GitHub page. This will let us select the ESP8266 board inside the menu item to install it. After the installation, the board should become visible inside the board's menu. While we are here, we can also choose the port to which the board is connected. To check if the board is working, we can upload a LED blink sketch. So far, so good. In order to run our matrix sketch, we also need to install some libraries. They are PxMatrix, Adafruit GFX, and all the libraries that are required, and ESP datetime. The LED Matrix datetime sketch can be found inside my GitHub repository. The link is in the description of this video. Because there are not enough pins on the D1 mini board, it needs to be wired in a particular way. That means that all the RGB inputs will be chained together by connecting outputs to inputs, and in this way, just one output on the board will be needed to feed in all the color codes. The chain of connections from the D7 output pin starts at R1 in, then it continues from R1 out to R2 in, R2 out connects to G1 in, G1 out connects to G2 in, G2 out connects to B1 in, and finally B1 out connects to B2 in. In this way, all the shift registers that are responsible for all the colors can be fed in from just one output. The connections are also described in detail on the PxMatrix GitHub page. Let me quickly connect all the wires and then we will take a look at the code. I have based it on one of the examples inside the PxMatrix called pattern test. It has a set of functions for initializing and refreshing the LED matrix screen. You can define the dimensions of the matrix and the scan rate, which is the number of rows that are displayed at the same time. It is the 32S from the panel properties that I mentioned earlier. Other panels can have scan rates of 8S or 16S. The date in this sketch is displayed in Roman numerals. There are a couple of functions that do this conversion. I have also added an Atari logo, which is defined here as a two-dimensional array. The date and time is fetched using the ESP datetime library from an NTP server. Inside the loop, everything is displayed using the Adafruit GFX library functions like display.print, and the logo is drawn pixel by pixel using the display.drawPixel function. Let's upload the sketch and see the final result. That's it for this video. I hope that you have learned something new here, and if you found it useful, please give it a thumbs up. Consider subscribing to my channel for similar content in the future. Bye bye.